Hey there, welcome to Calculus. I'm Quillen, and today we're going to be beginning our discussion of continuity by talking about discontinuities. So, sort of before we define rigorously and mathematically what a continuous function is, let's talk about why a function might not be continuous, what kinds of discontinuities it may have. There are four main kinds of discontinuities, or three main kinds, but one of them has a subcategory that is sometimes not considered as a subcategory. So depending on who you ask, it will either be three or four. I usually say three. So there are point discontinuities, there are essential or infinite discontinuities. Sometimes these are also called gap continuities, but the AP Calculus curriculum uses infinite in almost all contexts. And then the last kind is a jump discontinuity. And the functions that we discussed in that very first episode of this series, all of them, all three of these kinds of discontinuities show up in those functions. So first, let's talk about a point discontinuity. So as an example, let's say you have the function f of x equals 1 over x. And so you have this graph like this. Sorry about that cut. So let's say you have some function f of x that you know has a point discontinuity. Sorry about that cut. So let's say you have the function f of x equals x over x. And obviously that will simplify down to 1. So f of x will equal 1. But go with me on this journey of f of x equaling x over x just for a while. So let's take some axes and say 1 is here, 2 is here, and then, your points sort of like this. And then the graph of this function, which I will be sketching with this red line, will look something like this. But because we have an x in the denominator, when x equals 0, we will have a hole. And because we have that hole, the function is not continuous. When we draw this graph, if we had an infinitely small pencil lead, we'd have to pick up our pencil when we got to x equals 0, or else we would draw the graph incorrectly. So that means that f of x equals x over x can be said to have a point discontinuity. So even though it is identical in almost every way to the graph of f of x equals 1, the graph of f of x equals x over x is not the same. It just has the limit is just the same everywhere. And that is the essence of a point discontinuity, really, is that if you have a point discontinuity, you can take the limit at the point of discontinuity and it will still exist. So, say you have this function defined piecewise here, and it doesn't really pass the vertical line test, so it's not really a function, but it's just for the sake of demonstration. and it's not on these same axes necessarily. But then say it had a hole right here. Well, the limit coming from this side is going to be the same as the limit coming from this side. And so that means that this is a point discontinuity. A way to think about it, which is probably more intuitive, is that it's literally like you took a point and just plucked it out of the graph. Like you had a smooth, connected graph, not necessarily smooth in that there are no corners, but smooth in that it was all connected. So you had a fully connected graph, and you just plucked one point out of the middle. That is what a point discontinuity is. Next, let's talk about essential, infinite, or gap discontinuities, because these you will also probably be familiar with. You probably knew about point discontinuities from Algebra 2. You'll probably also know about essential, infinite, or gap discontinuities from Algebra 2, even though you may not call them that. So I'm going to draw another set of axes right here. But right here, I'm going to be graphing the function f of x equals 1 over x instead of x over x. So f of x equals 1 over x. And that will look, let's do it in yellow so it's different. And that'll look something like this. And in reality, it'll asymptote a lot closer to 0, but we can just say that we zoomed in a whole lot. But it'll asymptote right here and right here. It'll asymptote on both sides of 0. Now, you can zoom in wherever you want on this graph. You will never find the part where these two halves connect, because they connect at infinity. And because infinity is not a number, it's just an idea that makes math a lot easier to think about. These two graphs numerically never connect, or they're the same graph, but these two curves never connect with one another. And so they're not continuous because you have to pick up your pencil to draw them, no matter how zoomed out you are. But you also can't really, like, if you take the limit from this side and from this side, it doesn't exist. It's unbounded. And so it just kind of goes and goes and goes and goes. So that is what is called an infinite discontinuity or an essential discontinuity. I have heard it called a gap discontinuity because there's literally a gap in this space in here. And that gap stays the same no matter how high up you go. So an essential, infinite, or gap discontinuity is one where something goes to infinity and then it continues from infinity on the other side. And it can be positive or negative, and they don't have to be the same. So say you have, I'm going to do this in red. Say you have a graph that looks like this. That is still an infinite discontinuity. An infinite discontinuity is where that is the situation. It doesn't have to be at an axis. It just, one side of it has to go to infinity and the other side of it has to come from infinity. And either of those can be positive or negative, independent of one another. Now, the last kind is a jump discontinuity. And the only place in your precalculus functions that this probably showed up is your floor and ceiling functions. And because we don't really study those much, at least not where I'm from, it might be really unintuitive for you to think about these. But let's look at a jump discontinuity. Again, I'm going to draw a set of axes just right over here. And let's say that for these, f of x equals the floor of x. And you can write the word floor, open bracket x, close bracket, but the standard way is to just do that kind of square bracket like that if you are writing something out. And I'm going to do this in blue. As you know, that'll look something like this. Actually, I think I did ceiling. I think this is ceiling that I'm plotting, but it is okay. In fact, because I did ceiling, I'm going to go in and show you how to do that as well, how to write that. Because I know a lot of people don't know how to do this. So for ceiling, you just, instead of keeping the bottom part of the square bracket, you keep the top part of the square bracket. So you can probably guess based on this graph what a jump discontinuity looks like. I'm going to zoom in some. So let me grab my green. It's very obvious that like these don't go to infinity. They're not zooming down or zooming up. And they're also not connected with just a little hole in the middle. But it's obviously discontinuous because you have to like step and step and step and step. And so each of these steps you have to take is a jump discontinuity. So a jump discontinuity is one where it does not look like, let me rephrase. There's a visible, obvious discontinuity, but the graph does not go to infinity on at least one side. That's a jump discontinuity. They don't show up terribly often, so recognizing them and knowing their properties, such as that the limit from one side is going to be different than the limit from another, is more important than knowing them super duper well. Now, let's talk about removable discontinuities. So a removable discontinuity is a subgroup within point discontinuities. And these only exist in cases where the discontinuity exists because of the domain of the function. So if you have a piecewise defined function and the graph looks like this, and then there's a hole, and then the graph looks like this, and the pieces are broken apart right there, that's non-removable. But if you have this curve and it's all defined as one cohesive function, but there's a hole right there, then it is considered removable. And the reason they're called removable is because you can do algebra and the result you can achieve will be, let me start over. The result that you can achieve by doing that algebra will be a function with all of the same limits, no matter what point, but without the discontinuities. So if we wanted to remove this discontinuity from f of x equals x, we would just simplify it to f of x equals 1. If we had a line that was defined rationally and we wanted to remove a discontinuity right here, we could just change it to be equal to f of x equals x. So a removable discontinuity, you have to draw on your algebra that we talked about for the algebraic manipulation of limits videos, parts 1, 2, and 3, which was that mini series right before the squeeze theorem video. So again, removable discontinuities just mean that you can do algebra to it to make a continuous function. I hope that you have found these definitions helpful, and I hope that they've been at least a little bit interesting. But more than anything, I hope you will continue with me on this journey through calculus. This is Quillen signing off.